Well, okay, good. Yeah, first of all, thanks for Jose for introducing and for Jairo to put together this wonderful meeting. It's always exactly the right size to have great discussions and learn a lot. I'll be talking a little bit about elastic couplings in altermagnets and perspectives that we have seen. You will see there is in the philosophy quite a few analogies to what Kirill was just presenting in his talk, and we will just look at it from a somewhat different perspective. The work was done with a number of students. Charlie, who graduated now from KIT Keigo, came for actually 2 months and had a wonderful interaction with him. He came from the University of Tokyo. Iksu is a postdoc in Karlsruhe. Ans works with Raphael in Illinois. Gruger initially was in Karlsruhe, is now in Illinois. And this was a picture taken a while ago. And whatever the works you find here. So my understanding of altermagnets is that we have a system where the crystalline symmetries translations are unchanged, where I will get into this right away, time reversal symmetry is broken, where we have no net magnetization in the strict sense, and then we can soften that assumption under certain conditions if we wish so. And also often it's been discussed as states that are inversion even. And we all know that this is a result of this quite wonderful work done here by Libor, Haro, and Thomas. And it took me a while to appreciate the beauty of it, that you could so crystalline clear make statements even by going into this, if you wish, so non-relativistic spin limit, but you're making very sharp statements, and that I think has inspired so many of us. Very good. So there's another important paper that we need to discuss of certainly comparable importance, namely when we talk about broken time reversal symmetry, what I have in mind is the way Wigner discussed it. So therefore I do not see any reason to deviate from this. Über die Operation der Zeitumkehr in der Quantenmechanik, 1932, everything has been said. And nobody needs to redefine this as far as I'm concerned. So this is the way we will be looking at this problem. So then what else is there to say? Right, under those conditions that are listed here, the way that is easiest for me to rationalize things is to say, well, I mean, I just need to look at a time reversal odd order parameter. Because it breaks order, time reversal symmetry, that transforms under one of the E-reps of the point group, because there's no translation invariance broken in the system. And, well, it doesn't transform like a dipole, because then it would have a magnetization. And then we are done. And this answers the question, and then we also need to think a little bit what are the issues with this, just related to the discussion at the end of last talk. So let's say we have a tetragonal system, those are the E-reps, we all know them. If I want to exclude inversion, then, well, I would just take the odd parity away. If I want to exclude the option of a magnetization, then I would have to exclude the ones that transform like a magnetization, which is A2G minus in this case, minus being a time reversal odd, or EG minus for the magnetization in the XY plane. And this is it. And you see this is simple, and that's why I use it. But it's also dangerous because, for example, if you wanted to ask a question like what was discussed last lecture, when is a small spin-orbit interaction not really that important? Or when is a large spin-orbit interaction running the show? Then you can, of course, not answer this because you just don't, you're not sensitive to the statement. On the other hand, you're not making mistakes if you do it this way. So these are the ups and the downs, and we've all discussed it now. So from a strict sense, in a tetragonal system, then there would be exactly 3 symmetries only, A1G minus, B1G minus, B2G minus, and they would be the ones that I think have been coined by Raphael and his collaborators in this paper as so-called pure altermagnets. I hope So those are the states that would by symmetry not have a magnetization. And then, of course, you could have the A2G and the EG states, and they might have a magnetization. They might have a huge, say, D-wave component that could be all sufficient for the applications, as we have seen, of some of these spin splitting experiments, but there will inevitably be magnetization in the system. And that's it. And the beauty is, I know what point groups are, not much beyond it, so therefore I can get away with my limited knowledge in these systems. So the order parameter then can be most easily rationalized as having some object that transforms like an angular momentum operator and some form factor. And there can be all kinds of combinations of this one, and this is the natural description of the order parameter of such an Altermagnet. And to give you 2 examples, if I have a single band, then my non-trivial form factor transformation will, of course, only come from momentum dependencies. And that's why I'm indicating here you have a spin polarization at each given k vector, and it's just weighted in some L equals 2 fashion. And just to add to the confusion, this is, of course, L equals 2, so you would be tempted to call it quadrupole. And of course it's not, because it's an octupole, because there's an L equals 2 coming from the angular part and an L equals 1 coming from the spin part, and therefore this transforms like a magnetic octupole. And this is also the reason why I gave B1G here. Even though this is Kx, Ky, you would call this B2G naturally, but this transforms like A2G, and therefore the product gives you what this order parameter transforms like. So this is why this is easier for me to think about it like this, because it just makes it clear. If you have, for example, a Lieb lattice, then you just not only have a single band, and you have multiple bands characterized here by some Pauli matrices. They can transform non-trivially on their own right and can take over some of the, say, non-trivial momentum dependencies that you would otherwise get in these form factors here. So this is basically subsumed here in this one, just to give you a flavor. And I know we have seen this multiple times in many talks during this meeting, but it's still useful. So I will be talking about strain. So therefore, let's talk what strain is. Strain is ultimately given by the displacement vectors of positions that characterize in their dynamical version acoustic phonons. And just like the order parameter, they also transform under well-defined symmetries, whether you do not change the symmetry but merely change the volume, or whether you do change symmetries in well-defined ways or have a 2D irreps and so forth. This is here again done for a tetragonal system, and of course we all know how to do this more generally. Good. So then you ask, well, how can I couple with strain to this order parameter? And of course it's not possible without the help of a magnetic field. Why is this so? I mean, I was educated in the context of pneumatic systems, where we of course have a pneumatic order parameter that transforms just like strain, and then you can just multiply it. It's bilinear. This is a little bit different here because the order parameter of our Altermagnet is odd under time reversal. This is even under time reversal, so you need something that's odd under time reversal to make this term allowed. And then you need to think about what all these coefficients here are, because the representation of the order parameter, which we've just discussed, which I call gamma minus, the representation of the strain and the representation of the magnetic field all have to contain the triple representation, of course, to occur there. Good. And what you can easily see is if I take the derivative of the energy with respect to a magnetic field, I get a magnetization. And this is the much discussed piezo-magnetism. Well, to be precise here, this is the piezo-magnetism that is linear in the order parameter. I think we've just had a discussion that was primarily triggered by the fact that there can of course be higher order terms here. Yeah, good. So we have this is then the induced magnetization in the presence of an altermagnetic state once you deform the system slightly. Good.
So this is linear response.
Yeah.
It makes sense.
Yeah.
Okay.
Sure.
Did it always affect non-linear responses?
Yeah. We can add more terms. We can always add more terms. Yeah. So this piezo-magnetism will be useful for some of the aspects I want to say about the Hall effect. Okay, so then of course it's easy to visualize where all of this happens. We have, say, an upspin density and a downspin density, and once we are yanking on the system, then the balance between up and down will be distorted. There will be more of one than the other. This gives us a net magnetization done, right? That's all what piezo-magnetism is. So you can then go about and say, just to go back to this tetragonal group, and you can then ask, given an order parameter of a certain symmetry and the direction of the field, which strain do I need to apply? And that's just implicit in the group theory, and then you know, for example, what you have to do with your system in order to induce a given magnetization. Say here you would induce a magnetization in the x direction if you apply strain in the yz axis once you had an A1G minus state. Good. So you can also do the same, of course, in a ferromagnet. There's nothing that prevents you from doing this in a good old-fashioned ferromagnet, but there you always have a term where the order parameter couples directly to your field. There's an epsilon A1G here, but I could just drop that. It wouldn't have to stand there, right? It would just be allowed on its own right. That's why you would have a magnetization in the presence of the order parameter. Okay. So now this strain, and there are multiple effects that you can, how you can realize strain in a system, and we will discuss several of them. So this is the same term I've just given you, but a given strain, a second rank tensor, we have seen the elements, can either be because I have a phonon of a given symmetry that propagates to my sample, and it just chooses to be a phonon as we know and love it. But there doesn't have to be just a harmonic deformation of this strain. There can be topological defects of one side or another. You can have a disclination. You can have a dislocation, and so forth. They would, of course, also cause strain fields. They tend to be long-ranged, decay with power laws, and therefore you would have basically, by design, one-dimensional threads in your sample that would nucleate potentially in the presence of a magnetic field, the altermagnetic order parameter, if that's what you want to do. And of course, in any real material, you have defects and all kinds of things that would give you random strain. Locally, you just deform it as you have a vacancy or something that would induce a local strain field, and that is something that you can or may have to deal with, can also exploit. And this will actually be my first example, where we're going to look what can one do if you happen to have a material with random strain. Random strains are well established, for example, in affecting nematic order in iron-based systems. You just have a local defect that prefers one direction over the other. And that's the same what we need here. So the nutshell statement is actually quite cute, and this is something we did together with Ernst Chakraborty and Raphael. Suppose you have some Ising nematic order parameter. What I called phi is now called by it Pauli matrix tau, but there's no difference otherwise. So it interacts with itself, and there will be an ordering transition to which ultimately it's an Ising order parameter by symmetry. If it's a one-dimensional irrep that I've just discussed. And you can add some quantum fluctuations to this system. Maybe we have an insulator in mind where this could be relevant. You can then have an elastic term that is just the elastic constant of the system that gives you the energy deformation once you add strain to your sample. And then we have our piezomagnetic term, where I just shows here a certain realization where the magnetic field is in the z direction in order to polarize that magnetization in the presence of an adequate strain. Now what's interesting here is if you happen to have random strain, the altermagnetic order parameter doesn't see this randomness in the absence of a magnetic field. So because it just doesn't couple to it, at least not at leading order. However, once you add the magnetic field, you have a random field Ising model. And you have a random field Ising model presented to you, where in the same sample you can dial the strength of the randomness at your own disposition. Suppose, of course, that we have a sufficiently large coefficient up front here, but in order to see appreciable effects, but these coefficients vary wildly over materials, and we really need to learn more about the quantitative magnitudes of these piezo-magnetic effects in order to make progress along those lines. But otherwise, what you have here is a tunable random field Ising model. We all love the random field Ising model. Many have suffered on it. It is a problem that I will not attempt to solve because it's just too hard to solve unless you have computers and the people who do this as a professional. But just to give you a glimpse, what you can do is you can, for example, replace your interactions by mean field type interactions and solve the statics of the problem in this infinite range mean field problem, just to give you an idea of what can possibly happen. And what you see is happening here. We have here a properly normalized magnetic field and, say, transverse field. This would be the quantum critical point, if you want so, of this transverse field Ising model. This would be, and now you can, for example, get into the, have a transition from an altermagnetic state into a paramagnetic state triggered by the changing of disorder. You can do the same as function of temperatures. So you would have, at a given, depending on the strength of the disorder, you could destroy your long-range magnetic ordered state and have a random field Ising transition. Yes? No, the random, so you have both. You have a transverse field model, maybe I just misspoke. You have a transverse model that is non-random, and we can also discuss whether you could have strain fields in the, but then the magnetic field direction would have to be a different one. But if you choose your magnetic field appropriately, you have a chance to have a transverse field non-random Ising model, or you have a classical Ising model for that matter, and you have a random field longitudinal. Of course.
So the question is, are you in 2 or 3 dimensions?
3, of course.
Okay, in 3 dimensions, in principle, there should be a phase transition.
There should be. In 2 dimensions, we know there's not.
There were infinitely many fights. Some of them physical.
Yes. I want to know everything about that.
Okay. Yeah, so in principle, in 3 dimensions, there's some debate about the nature of the transition.
Yes, yes. No, they're not in 2 dimensions. This would not make any sense.
No, but even in 3 dimensions.
In 3 dimensions, I think there's good indication that there is a transition.
Right, but depending on the measure, sometimes it looks first order, sometimes it looks second order.
Right. The reason is ultimately because the dynamics of this transition is super complicated, and nobody should attempt, and nobody has attempted to describe the dynamics of the finite dimensional system in terms of the infinite range model. But I think to get an estimate of whether, what's the order of magnitude of the transition is, this is a fair calculation.
I disagree with that.
So you can, for example, see implications of this one when you have look at the elastic constant. The elastic constant of the system in the absence of the field should, for example, be completely unimpressed, or at best have a little jump at the transition. But in the presence of a magnetic field, you would then soften your system, and depending what the degree of coupling is, you would have a random field suppressed elastic constant that could make the lattice critical at this transition. Just to give you one example, another quantity that we will be discussing when we move on is the elastocaloric effect, which is an experimental approach that has gotten quite some traction recently, pioneered by Ian Fisher in the context of correlated electron systems, and also the Max Planck group in Dresden around Andy McKenzie and Elena Gatti and a number of others have done wonderful work there. What you do is you change strain in the system. You try to do this adiabatically, and this will give rise to a temperature change in the system. And if you then use your thermodynamics, you find that this gives you the ratio of the entropy derivative with respect to strain divided by the entropy derivative with respect to temperature. The latter has just been expressed as terms of the heat capacity. So what you see, you can get the entropy landscape in the system and map it out, and it's a rather interesting and susceptible quantity. And again, the elasticaloric effect here at this transition will not diverge, but it will have a cusp. At this transition, we haven't calculated this in the ordered phase of the random field Ising model, just because we're too scared of doing this for reasons that Eduardo pointed at. But clearly, this would be another quantity that is now in operation for altermagnets that could tell you something about these systems where you can field tune the strength of randomness in a system. Just to, in the same spirit, look at these different contributions of strain effects. Another option that is rather interesting is that the coupling to lattice collective to phonons, which are ultimately gapless degrees of freedom, if they are acoustic phonons, changes the character of the altermagnetic order parameter itself. So it changes the range and it changes the character of this interaction. So these changes are probably most prominent if you...
Can I ask you a question?
Of course.
In this random strain, can I also put there issues like, for instance, domain walls? And because I'm going, if I have...
Whatever you wish.
So this is all included in this one term. Okay.
Yeah. Mm-hmm.
I have a related question. So you mentioned correctly that because elastic fields have long-range character, in principle, it's not just a local random field.
It is not. Oh, I would
so
not.
The random field will be correlated over fairly long distances.
I would not want to describe a dislocation in terms of the random field that we have just treated here. Yeah. This would be a local vacancy that locally changes the rotational symmetry. Because it's not at a rotation symmetric site. If I have a dislocation, then I would have to treat that dislocation. In a different context, we actually did treat the effect of dislocations and potential time reversal symmetries in superconductors as a consequence of this one. Because of the long-range strain field, and you mix order parameters of different symmetries, and you would definitely nucleate magnetizations near dislocation, and of course the altermagnetic order parameter, just because you break the...
But simply even given the fact that you get these power laws,
it's a big effect.
So it changes the nature of the random field Ising model problem as well.
Yeah, the random field Ising, as I said, the random field Ising model was done for a material where we have treated it for so long that it doesn't have any dislocations anymore. Yes.
Wait.
Thank you. Does your model includes magnetostriction? Because if you have a piezomagnetism, you should also have a magnetostriction. And it looks, you should.
So magnetostriction, you're meaning this would be a higher order term in the coupling to the I just need to have it translated in my brain. It is a higher order term in the order parameter, right? So you have a quadratic...
It's the same as piezomagnetism.
If it's the same, then we have it because we have it. If it's different, then we can...
I haven't seen it anisotropy in your case. And
anisotropy of what?
Magnetic anisotropy.
Of course, you have an Ising order parameter. I didn't tell you what that order parameter is, but I told you only a certain magnetic field direction can couple to it. This is only possible if there is an anisotropy to begin with.
Okay,
yep.
Thank you.
Good.
Just a quick comment about so if you have enough dislocations, they start screening each other. And actually, in a different project, we looked at, you start getting a Gaussian distribution, but the price you pay is that you need a lot of dislocations to do that. So there is a limit where we can defend ourselves in court.
Yeah. This is all very interesting. But yes. So here we had in Raphael's talks a discussion of an itinerant altermagnet, and where he and his collaborators looked at the possibility that the fluctuations of this ordered altermagnetic state would then, for example, induce superconductivity, and we've seen that this could give rise to singlet or triplet superconductivity depending on interesting details. I want to look at the normal state here. And in the simple, plain vanilla version of this quantum critical point in a three-dimensional system, actually, we know more or less what it happens because it should be identical to the one of an Ising nematic transition. And for the Ising nematic transition, we also know that in the electronic language, there will be a heat capacity coefficient of the electronic specific heat that will diverge logarithmically. Fine. This is very interesting, but unfortunately it is, for the nematic case, not what you get. In the nematic case, we know, and this was pointed out very nicely by Indranil Paul and Markus Garst a number of years ago, as soon as you couple to the lattice, the system behaves differently and you recover the good old-fashioned Fermi-liquid behavior. This is because these long-range strain forces that the phonons mediate suppress fluctuations significantly, and you cannot treat it this way. I'll show you the details in a second. The altermagnet is much more interesting to that extent because in the absence of a magnetic field, you don't have that effect. So the altermagnet should actually be one of the very few realizations where you see this logarithmic behavior of the heat capacity coefficient. Now, what is causing this? Where is this coming from? Because in the magnetic field, again, we can reintroduce this very same strain coupling, and we can tune off and on the possibility of having linear heat capacity going with a log or not. And the physics underlying is basically the following. If you look at the susceptibility either of the nematic or of the altermagnetic state, at its critical point at zero frequency, you would naively think there's some q squared term and then you may be accumulating enormous dimensions. But the coupling to strain gives you basically non-analytic or direction-dependent terms that tell you, really, I will only get soft if I'm approaching my long wavelength limit in a very well-defined direction. This is the direction along which the sound velocity of the lattice actually gets soft. The sound velocity of the lattice doesn't get soft along all possible directions at a second order phase transition, and that's what causes this. So for example, go along the QX direction in Q, then you see this here is 1, and you can never make it 0, even if Q goes to 0. So you always stay massive if you couple to this elastic problem. So therefore, I have 4 minutes. But, well, I mean, this is negotiable here, right? So, and... so what we looked into this, and it's actually something quite cute happens. So if you happened to have this strain coupling, either field-induced or present in a nematic system to begin with, the single particle properties then become Fermi liquids again. But the collective modes of the system and the elasticaloric effect in particular still have a logarithm. So you can see that this state is critical in a well-defined way that is different from a good old-fashioned Fermi liquid. Yes?
Sorry, this is
No.
Raphael is... Where is this? Is this in the Fermi liquid phase or the quantum?
This is the behavior here. Yeah, and here it would be t to the minus 3/2 divided by log.
So how can I rationalize? Does it mean that I have a different dynamical exponent, or that I have a dynamical exponent that is changing as function? Like, because it looks everything else like Fermi liquid, but is not the Fermi liquid fixed point. So how should I think of that?
So basically what you have these elastic coefficients, you can write down a scaling theory of this problem. You can see that basically since you're getting soft along only certain directions, so because the velocity is soft, it looks like you're living in a different dimension. You write down a scaling theory of the problem, and what you find is that the heat capacity, the critical contribution is subleading to the Fermi liquid one, while for the elasticaloric effect, the critical contributions are the dominant one. So therefore, this is a non-trivial fixed point, even though the quasi-particles are well defined, which is a case I at least don't know, but maybe Eduardo knows.
No, I don't. But I have a question. When you have this anisotropy, typically, you may have different scaling exponents depending on the direction as well.
If you want to introduce them, yeah, that's what this is here.
No, I know, but when you do the scaling hypothesis for the singular part, you only include just C, and then it's isotropic in the plane. At least
Of
as
the
far as-
rescaled problem.
Right, but in general, you have different.
You could, but
attachments.
at one loop we didn't find any indication for this.
Okay, but say in many, as you know well, in things like
Yes.
liquid crystals and so
Yeah,
on.
this could happen, but it doesn't happen at one loop.
I see. So is that an accident? You
Yeah.
think? Is an accident?
I
Is
think
it
so.
similar?
It's probably there two loop.
Okay.
Yeah.
All right.
So I need to move here because now I wanted to talk about something else, namely the Hall effect in the system, because it's been discussed quite a bit. We know how to get an anomalous Hall effect in, for example, a magnetic system. There's a wonderful review here. Some of the people of the authors are in the audience. You need to calculate the Berry curvature of the system, then you get an information about the anomalous Hall effect of a system if it either breaks time reversal or inversion symmetry, and that we are all very, very happy with. You can easily show that with this classification scheme, this would only happen if the system also has an added magnetic moment. So there will be no anomalous Hall effect in an altermagnet if it has a zero moment, right? It's, I think, quite obvious, but it's worthwhile understanding why this is happening, because the Berry curvature of the system is not vanishing. It's just has a specific symmetry, and if you calculate it, this is a calculation for the leap lattice. I'll give you some details in just a second. You see there's a Berry curvature quadrupole of that system, and now you see what you want to do. If you're distorting the system, you're just distorting the balance between the the red and the blue parts, or the plus and the minus parts, and you can get a finite response, while of course in this perfect geometry without strain you don't. Yeah.
So just the statement you made that that you get it without you have to have a moment. You have to be in a magnetic point group that allows for a moment. If you calculate it without a moment, you still get finite one.
Well, I mean,
Okay,
I can,
just
for
to
example,
be clear,
yeah, of
yeah.
course, but I mean, I can distort my moment in a direction where it's not supposed to be in equilibrium. Then I would get a finite, for example.
No. Even in the one that you're allowed to have with the moment, like magnetic telluride, if you do the exact calculation with zero moment, completely aligned, completely compensated, you still get a finite.
Yeah, but that's because the moment is in principle allowed.
Correct.
It just happens to be.
But you make a statement, exactly. You just made a statement that they had to have a moment. It has to allow for a
Yeah, but
moment.
for me, aesthetically, this is fine tuning. So this is, yeah. Yeah.
I mean, it's the same thing. By the way, incidentally, it's the same thing. Sorry, I have a strong voice. It's the same thing for. Oh yeah, it's the same thing for the circular dichroism. Right, circular dichroism is only allowed if the moment is allowed. If the moment is zero, you get zero-sum rules on every edge, so you have only oscillations, but you still have a signal.
But I mean, the moment can be zero and still get the signal.
Yes.
Oh yeah. But zero by coincidence.
Zero by coincidence means fine tuning for as far as I'm concerned. I mean, whatever. This is the dictatorial principle, right? What is allowed is going to happen. Yeah. Exactly.
Experimentally relevant systems are fine.
Yeah. Oh, yeah. The world can be fine-tuned in many, many different ways. Yeah. But group theory doesn't help us then, right?
So, flip as a symmetry, then the Hall effect vanishes.
You need to say more?
No, just.
We are in the discussion time.
Okay.
I'm almost done here. Yeah. So, well, what we said is, well, you need to yank the system a little bit, because this one would be vanishing for what I call pure altermagnets, and this is, I think, without debate. And therefore, the question comes when is the next leading order term, when you have a strain problem non-zero, and you can basically think about it in two different ways, right? On the one hand, you are inducing a moment, and the moment itself could give you an anomalous Hall effect, period. But what you can also think about is how the Berry quadrupole actually gets deformed. And that is a different phenomenon to think about. The way you do this is straightforward. You add strain terms to your coupling. You have what is essentially an electron phonon coupling. You check how the Berry curve changes. You analyze, you look. And that's what you see, right? You deform the quadrupole in a well-defined way. These dashed lines here are the zeros, and this is the difference. And then you can see that in this, for example, leap lattice calculation, you can get a finite elasto-Hall effect, of course. And what's interesting is maybe the order of magnitude, because this has the dimension of a conductivity, and therefore it can easily be of order e squared over h if you're in the vicinity of a Dirac point, albeit gapped. So that's kind of non-trivial, because even if you multiply it by 10 to the minus 3, because the strain is small, this is still clearly a detectable signal in these systems. And here we discussed that, you've seen this yesterday, that the magnetization is of course also induced, but its contribution to the barrier curvature is there. Of course it's there, but it will not have a quadrupolar component. It will just have an induced S-wave component. Which one is the dominant one depends on details of the calculation, and we can't really tell. So because I mean, I wanted to show the biggest table of this conference, so I thought those are all the allowed elastoconductivity terms for whatever the different symmetry groups of so-called pure altermagnets and the corresponding magnetic point groups, and we are super, super proud that we can operate Mathematica and LaTeX sufficiently well to draw these lines. And and this is basically what I have to say about.
This is not the biggest table.
Huh?
The audience is afraid that this is not the biggest table.
There will be more, there's more to come, right? So this is the piezomagnetic effect. I will skip what we had done also, which is the dynamical coupling, how you can see the altermagnetism in the phonon spectrum by a symmetry analysis of the phonon spectrum, and the mechanism is very simple. You don't always have to couple to the order parameter. If it's a dynamical degree of freedom, you can couple to the conjugate momentum of the order parameter. Every order parameter that odd under time reversal has a conjugate momentum that's even at the time reversal. You don't need a magnetic field to couple to this object. We have calculated this in detail and find that you find coupling, level repulsion of phonon spectra, and symmetry dependent traces of the altermagnetic order parameter in the phonon spectrum and phononic contributions in the wave function at the actual energy of the altermagnetic paramagnon, if you want so, which is one way to measure these objects in an experiment. So I can conclude, if you are distorting the system, there are all kinds of interesting effects you can use with strain coupling. It can be exploited to detect and to manipulate altermagnets. Thank you so much for your attention.
Thank you very much. Your questions, Ellen.
Very naive question. Can you give an example to this momentum, conjugated momentum? For example, I have an order parameter like magnetization with something which you introduced. What would be the conjugated momentum? How can I physically see it? I mean,
well, I mean, it is. So of the order parameter itself, it has to be. See, I know it for a couple of cases. Do you have a good idea? I mean, it's it's the angular momentum, right? But that's what I just said. But that's not what we have here, right? Yeah. Yeah. Yes. So I can write it down in terms of, say, phonon operators that would naturally. It's a transverse field of that problem. Yes. Yeah. Yes. Yeah, there has to be an object that doesn't commute with the order parameter, and we have the order parameter in some fermionic representation. You can always find which combination of fermionic degrees of freedom. Yeah, yeah, but it's a good question to which I don't have a good enough answer.
Thanks a lot for the great talk. I was wondering also on this dynamical coupling, is this a coupling that requires spin-orbit coupling? Because otherwise you wouldn't ever see it in the phonons, right? Okay.
And second, okay, Livo, and then I'll come here. Oof. And then. Okay.
Thanks, Joerg. So, what is the conjugated field to null vector? Null vector.
It's a ferromagnetic moment. Yeah, that's Haldane.
Sorry. So. Okay. Okay. Okay.
So there is one more here and one more here.
Thanks for the really nice talk. So can you justify a little bit more that you picked an Ising coupling?
Any one-dimensional irreducible representation will be an Ising model, period, because it has a one-component order parameter. If it is a two-dimensional irrep, then I have two-component order parameter. In a cubic system, I may have three-component order parameter. That's all I can get. But the vast majority of all the order parameters that we have discussed here are one-dimensional irreps, and therefore this is an Ising order parameter. Now we can discuss what happens in the absence of spin-orbit interaction. Then this Ising variable is gapless, and then this is a different story. But I am in the limit where spin-orbit interaction is present, and for the critical behavior, this gap is important.
Okay, thank you.
Okay, so this was your question. Okay, so Paolo.
Hi. So, first of all, one remark about one-dimensional representation. Just let's not forget that all cyclic groups have only one-dimensional representation because they are abelian and they are complex, right? So that's just an aside. The question was about coupling to phonons. So obviously phonons, if you want to couple in that way, they have to be parity even, like strain. Correct. So they're not optical phonons.
Acoustic phonons.
But
the acoustic phonons here.
Sorry, I said something wrong. They can be optical phonons, but they cannot couple to light because they don't have a dipole moment, right? So I just wanted to point out that maybe you can comment on it.
Well, they can couple to light, but in Raman experiments. Yeah, this is also light. Yeah.
Okay, are there more questions for? Yes, Tomasz.
So in your anomalous Hall effect, you have spin-orbit coupling, right? Yes. Yes. Okay. Just to clarify.
Of course.
Because without it,
it wouldn't make any sense otherwise.
Okay. Then, thank you very much. I think we are on time.
Here we go.